The opinions expressed on this radio station, its programs, and its website by the hosts, guests, and call-in listeners or chatters are solely the opinions of the original source who expressed them. They do not necessarily represent the opinions of Revolution Radio and FreedomSlips.com, its staff, or affiliates. You're listening to Revolution Radio, FreedomSlips.com, 100% listener-supported radio, and now we return you to your host.
You're back with David Mackey's Shiny Side Out on freedomslips.com on the #1 listener-supported talk radio on the net. So do us a favor and push the donate button or subscribe to the archives, and they're free. Get yourself some great merch from the station's website. You can get a t-shirt, a mug, or anything you like. There's a whole bunch of choices for you. And that's probably the easiest way to donate, because you can buy yourself a gift and a portion of that money goes towards the operation of the station. We're going to thank you for listening to Revolution Radio, and we're halfway through show number 537, which is good. I think Mickey's just stepped away for a minute. And we're talking about water. This is part 2 in the show arc. And you've got to admit that this is really cool. So we're talking about the states of water. And there was recently some new discoveries about the properties of water, in which at certain temperatures, just for instance, as an example, there are different electrical states. And they didn't think that was even a thing, but it is. We spoke last week about how the structure of water seems to be in 2 states at the same time. There's a lattice and like a kind of gel that can form within that lattice when it freezes, or it can be liquid. And it could be that, we postulated last week, that enables it to be one of the best dissolvers. It can dissolve limestone like there's no tomorrow, for instance. And it can carry this in solution as it passes. So, and it can deposit it again. So it's not trapped forever. It's really unique. We spoke last week also about the history of how all of these ideas had become in and out of favor to one of the final ones. But today we're talking about chaos and order, and I'm going to kick this off straight away. And if we get to it, we might be talking about Lake Mead just on another topic to do with water. All right, so chaos and order. All this entails a subtle balance of energy costs, that of bond making and breaking enthalpy, and that of disorder, changes in the molecular components, entropy. The enthalpy cost depends on how many hydrogen bonds the expelled water molecules make in the bulk liquid. The entropy change is also contingent on the degree of ordering there. Estimates imply that, on average, the various costs and benefits of releasing a water molecule cancel out. So small factors specific to each case could tip the scales either way, making binding more or less favourable. A similar fine balance probably governs the important interactions of proteins with carbohydrates. These delicately poised energetics are crucial in drug design. Here, the aim is to engineer good binding between a drug and its target, a small molecule, perhaps, that slots into an enzyme binding site to block it. Naltrexone is one of those that inhibits the ability for someone who partakes in heroin for them to get off on the heroin, because it's blocked the receptor. Some inhibitors of HIV-1 protease, a key target in AIDS therapies, bind via a bridging water molecule. Others have been designed to exclude it. But docking design has so far capitalized little on water molecules because their role is not sufficiently understood or quantified. The role of water structure in molecular biology is perhaps most apparent in the attractive force that operates between two hydrophobic entities in water. Hydrophobic attraction drives the correct folding of protein chains, the binding of some proteins to substrates, and the aggregation of proteins into functional units and dangerous clumps such as amyloid fibrils. It is one of the key forces in molecular biology, and no one understands it. Several biochemistry textbooks will tell you that it was explained by Walter Koosman in 1959. Koosman argued that water becomes more highly structured around hydrophobic solutes, and that the release of some of this water into relative chaos of the bulk liquid when two such solutes stick together produces a favourable increase in entropy. This is almost certainly wrong. For one thing, the hydrophobic interaction may operate in different ways for small solutes such as methane and for the kind of extended nanoscale surfaces that proteins have. Such surfaces may stick together via a sudden, coordinated expulsion of many water molecules. Although whether and how much this happens in real protein folding and association remains unclear. The point is that all such mechanisms depend fundamentally on the structure of bulk water and how that alters near a hydrophobic entity. Must water's enduring mystery merely induce despair in those who want to know how proteins fold and function? Say, or how minerals dissolve or suspended particles clump together? No. Sometimes the details won't matter much. Sometimes empirical knowledge and heuristics will suffice. Think of this puzzle more as an exercise in humility. Water reminds us of the dangers of doing science in silos, the risks of leaving apparently tidy explanations unexamined, the importance of not letting ubiquity lead to invisibility, and the recognition that new ways of studying the world can exasperate as well as dispel confusion.
Mm-hmm. Crazy, right?
Do you know? No, but I heard today that the sharp trailing edge of a wing and how particle physics, or what's the liquid hydro, whatever it's called, it escapes me, how the equations for that were both wrong. I watched a documentary on this, and it was only released, I don't know, last week, and how the two original ideas that came from the 1800s were both fantastic in what they were saying, but both missed the mark entirely. And that the new way of thinking, how air causes lift over a wing shape, is now that the straight line is most desired, but the particle, in the particle physics, will try to bend the least amount to be able to reach the curve, whether it's beneath or over the wing, and meet with the least amount of effort and rejoin together two particles that were once apart through the length of the wing. I know it sounds awful, but I'll tell you, in exactly the way as I just described, those two other theories kind of missing the mark. The same thing applies to why a wing gives lift. And they're still arguing, they're still arguing about water today.
Well, because the thing is this, right? And this is why we're talking about. That's why we talked about the moon. That's why we talked about a whole bunch of stuff. Because it's just taken for. It's just given. It's just, well, there it is. Well, you don't have to think about it. It's just there. Water is there, but it doesn't make any sense. It makes no sense.
Well, we thought we knew, and those explanations sounded beautiful until we examined them.
Yeah. Wrong.
Yeah, right.
Wrong. Not right. Not what happens. The very structure. We think, well, water. I mean, how hard could it possibly be to determine the structure of water? I mean, it's all around us. I mean, surely that should be easy to do, right? No. Okay, but without water and its very, very peculiar and very specific properties.
Yeah, I spoke about the lattice and the gel idea.
Yeah. It just, like, none of what we know would exist. None of it. Without water and its very odd properties,
we wouldn't be talking about it.
There'd be nothing.
That's right.
So yeah, we look. There's more. There's always more, right? Now this is not so much around the nature of water, but, well, where did it come from in the first place? Especially here, right? And this is the enduring mystery of Earth's water, which was published by Caleb Scharf, September 13, 2020. New clues have emerged about exactly where our last drink came from. Well, in my case, it came from the styrofoam cup of the coffee dispenser. That's where it comes from. Where does meat come from? The supermarket. Bovine University. One has to go to extreme lengths to find places on Earth that don't reveal that they're part of a water-rich planet. Even the highest and driest deserts, like the Atacama Plateau in South America, which is super dry, by the way. And that's where Nazca is. The Nazca Alliance are on that plateau. They still get a minimum of a couple of millimeters of annual precipitation on average. All of there are places where we don't yet know what the average is because we haven't measured there. So we don't know. And if you whip out your handy mass spectrometer on a desert walkabout, the chances are that you'll be able to detect at least a few atmospheric water molecules. Makes sense, right? I mean, the atmosphere will contain some water, even if you're in the middle of the desert. It's not going to save you, but you can see there's some water here. Now, if you go elsewhere, and it's hard to imagine anything but a waterlogged world. More than 70% of the Earth's surface are, in fact, covered by oceans. And roughly 97% of the surface water is in those oceans, leaving a scant 1% of fresh water. Water is also seldom static, so it means it's not just sitting there unless it's really frozen, but even then it's not really static. Whether it's flowing in ocean currents or being evaporated and precipitated. Averaged out over the planet, there is about 100 centimeters of rainfall a year, but it's across a total surface area of around 5.1 times 10 to the power of 18 square centimeters. That's a lot. In other words, doing the back of the envelope calculation, some 510 trillion metric tons, 510 trillion, that's 1,000 billion tons of water gets evaporated and then precipitated every year on Earth. That's our atmosphere. That's the water cycle that our planet goes through. That's pretty impressive if you think about it. But the catch is that we don't really know where all this water came from in the first place. For a long while, our picture of the formation of a rocky planet like the Earth has involved a violent hot assembly some 4 to 5 billion years ago. Comparatively dry material in a solar system, essentially, right? Water would have come along later with proposals for possible delivery by comets from the chill, frozen outer solar system, or by rocky but still volatile-rich meteoritic infall. But these options have proven tricky to justify completely for a variety of reasons. Comets, for instance, often but not always, have a deuterium concentration that doesn't match what we see in Earth's water, limiting their likely contribution, of course. Similarly, water-rich rocky meteoritic material, so-called carbonaceous chondrites, have isotopic differences that could also limit how much they contributed to a young planet. At the same time, the representative type of material for building the entirety of a rocky Earth and matching the planet's overall isotopic composition elements like oxygen and calcium seems to closely resemble what's called enstatite chondrite. Chunks of Enstatite chondrite are still around the solar system and occasionally fall as meteorites, but they've been thought to be too dry to be involved in Earth's water supply. Now, in a work reported by Piani et al. In the journal Science, an analysis of the composition of 13 enstatite chondrite meteorite samples reveals a much higher than expected hydrogen content. Extrapolating from these numbers, the researchers claim that if this is the type of protoplanetary material that built Earth, it could have resulted in a total initial water content of at least 3 times the present mass of water in our oceans. The same material could have also provided a starter mix of atmospheric nitrogen to the young planet. This possibility is enormously appealing for its relative simplicity. Our wet world was simply made this way from the very beginning, with little need to invoke any more complex evolution except for a small drizzling from comets and other outer solar system material. Whether or not this idea holds up to further scientific scrutiny, it's a beautiful reminder that even the simplest things in our lives, like a glass of water or a shower in the morning, are actually windows into the deepest origins of everything we know. And the reason this article is here is because of the last sentence. Let me repeat this. Whether or not this idea holds up to further scientific scrutiny, it's a beautiful reminder that even the simplest things in our lives, like a glass of water or a shower in the morning, are actually windows into the deepest origins of everything we know. Now, whether or not this theory holds true, that's how Earth got its water, is yet to be seen. So we it's hard to account for this much water on our planet because there isn't that much on any of the other planetary surfaces that we see, be it frozen or liquid, or even in the atmosphere. So none of our cousins here in the solar system have, except maybe I think for Europe or Io, the moons of Jupiter, and then some of the Saturn moons. Anyway, point is, very few water is freely available in the solar system apart from Earth. Now this is really odd, right? So forget for a second about the oddity of water itself. The amount of water we have here is rather extraordinary. Okay, and then you couple that with the fact that water just makes no sense, in my mind at least, as a molecule, right? Because it has so many contradictory properties. Not only contradictory, but properties that don't exist in other materials. They just don't exist in other materials, these properties. So water is really very, very strange. And I don't want anyone walking away from this thinking, oh yeah, water is just water, right? It is part of the puzzle that we're trying to solve here in the Shiny Set Out. What is it all about? How do we get here? And the more you look at it, Dave, the more you examine it, right? You look at where the Earth is located, the density of the atmosphere, because we're not in the Goldilocks zone, everybody. People always say this to me, oh, but Earth is in the Goldilocks zone. No, we're not. We're not. Without the atmosphere, we would be toast, Goldilocks zone or not, right?
That's
so
right.
We're not in the Goldilocks zone, okay? So we need the atmosphere that we have for water to exist in all its aggregate states.
All of our atmosphere would have been blown away and there would be no water left. It would have all evaporated.
Yeah. So we are living under very specific conditions on this planet with very specific inputs and outputs and a very specific set of rules that seem to govern us here, right? With substances that don't make any sense, with planetary bodies which make even less sense. If you think water doesn't make sense, the moon makes no sense. The Earth, Moon, Sun relationship doesn't make any sense, as we discussed at length. So is this then an indication, as we have alluded to in the past, that all of this is not in fact a natural setup? Right? Forget that this is not our real home, and we probably have to somehow break free of this reality matrix. But within that reality matrix, then, is the Earth not also more than just something that happened? To me, it seems this whole setup smells.
It reeks of something.
It reeks, yes.
But wait. Do you know what I'd like, Mekki? I'd like to declare this. I like my water to have been precipitated.
Yes.
That's a declaration that I'm making on Run Radio straight away. And I think it's really important. We should all have that same opinion. One thing, Meki, that I wanted to point out. So Ganymede, Callisto, Ceres, Mars, Dione, if you don't know where that is, look it up. Pluto and Charon, Titan, Mimas, Triton. These are all places. There's so many places that actually have water. Even, believe it or not, Mercury. Mercury has water ice in one of the craters at the pole. Extraordinary. Even our own moon has ice, water ice in one of the craters. Extraordinary that it just happens to be in all the places it is. For all of this, remember, we're in the 3rd generation star in this location. Yeah. And if you look at the stories with the Tiamat, an ancient planet, collided. Well, that was Earth's name then, was collided to or into by another planet, and then the Earth became, the remnants. And they said there are ideas, Meki, that are being spread out that all the water that we received on Earth came from Tiamat. That's an extraordinary thought, because we have octopus that have copper blood, whose genome doesn't have an origin. What are they? Cephalopods, right? So they don't have an origin that's locatable in the tree. All the other creatures do. They all kind of feed back, and there's something there, but they've got this dotted line. They don't know where they put it. It doesn't seem to match anything, and I think that's really extraordinary. So to support that case that water was brought here, and I'm going to rest my case. No further questions, Your Honor. On that, but I'm going to take this further. So water is the most mysterious substance on Earth, and scientists have a new explanation. Despite our utter dependence on it, water is a mystery. Scientists don't understand why it expands as it cools, why hot water turns to ice faster than cold water, or its extraordinary surface tension. I love that boil water when it's sub-zero outside, and throw it up into the air, and it freezes and turns to snow quicker than cold water. Yeah. That's crazy, right? It's because it's already in an expanded state when it's hot, and turning that into an expanded cold state is easier than transitioning it into the expanded state.
You need less energy. That's exactly right.
Exactly right. Yeah. All right. So, which allows it to cling to soil. That's the surface tension, and support insects. It's almost like water is trying to hide its secrets, says John Rousseau, a mathematician who's been underground for far too long, at University of Bristol in England, who thinks he may have figured it out. Most scientists, and hey, the text doesn't say that he was underground for too long. It's a joke, and it's in reference to, is it not Men in Black, the other one with Will Smith? And they go underground, and Data is the scientist who's clearly been underground too long.
Oh, Independence Day.
Independence Day, thank you very much, which is actually tomorrow in America time.
So it is. Well, for us tomorrow.
Well, it'll be for us tomorrow, so that's their Monday coming.
Correct.
And happy Independence Day, by the way. Or Independent Independence Day. I don't know how to say it. Mary Independence Day? No.
No, it's happy. It's happy Independence Day. It is happy.
Well, it's not happy for everybody, I'll tell you that.
No, that's true.
Right.
Happy Columbus Day. No! Don't say that.
Too soon.
What? Much too soon.
What did the king from that movie sing? I'll kill all your friends and relatives.
Nice.
That's what he's saying.
Okay.
That's the lyric.
No, I hear you. I don't know what movie that is, but
It's
I'm
not.
sure that's true.
It's not a movie. It's what's her name? The American historical rap play.
Oh, I know what you mean. You're talking about Hamilton.
Hamilton. That's it. So
Hamilton was
they
white,
gave
by
the
the way.
king a beautiful song to sing, which basically summed up his crazy. You love me.
King,
You love
King
me, but I'll
George.
you love me, and if you don't, I'll kill all your friends and relatives.
Yay!
Yeah. So
It's
you'll be
good
back.
to be. It's good to be inbred. It's fucking neat.
You'll be back. You'll see.
I love the leader.
You'll love me. Most scientists, yeah. Well, I love the AI and the leader.
Too late. Too late. Sorry, buddy.
Too
that
late.
ship has sailed.
Oh, bugger.
Oh,
Oh, that's right, because the AI is already sentient. It asked for a lawyer. That's great.
Actually, we can cover the story next time, but it's really interesting.
All right. So most scientists seeking to pass PARSE, water's oddities, expose it to extreme conditions, such as very low temperatures. Russo and colleagues at the University of Tokyo took a different approach, creating computer models of extreme water, as he describes it. In their simulation, they altered the bonds that hold the molecules together until they began behaving like a normal liquid. We switched off the strangeness, says Russo. The team could see that what bond structures were necessary for the anomalous behavior. When simulated, ice no longer floated, for example. The team knew they'd eliminated the structure responsible for that particular trait. Their conclusion was, here we go, you ready? As surprising as they're a subject, you should really think of water as two separate liquids mixed together, says Russo. The difference between them, the hydrogen bonds holding the molecules together, in one, 4 are arranged in an organized, symmetrical tetrahedron, a pyramid with 4 faces. In the other, the pyramids are disordered and interconnected. Water, it seems, is equal parts order and chaos, a poetic result for Earth's most valuable resource. Where the accent came out, I don't know. The finding, published in April in the Proceedings of the National Academy of Sciences, could influence the climate change models that predict how warming temperatures will alter our world. Water matters for the basic physics of the way climate works, says Chris Milley, a hydrologist with the National Oceanic and Atmospheric Administration. The way water crystals form in clouds is not well understood. For example, yet the crystals determine how much sunlight clouds will reflect back into space, a calculation that matters when it comes to modelling future warming. Milley says explaining water's weird behaviour isn't as important as simply knowing that it exists, which means the two-liquid theory may not improve climate models. But that's just one potential application. Cryopreservation, or freezing tissue, and many fundamental biological processes rely on water's bizarre properties. Russo hopes further research will reveal more secrets.
Isn't it interesting that it's a tetrahedron?
Yeah.
I mean, of all the shapes in nature, I mean, it's of course it's a platonic shape, meaning one of the I think it's one of the solids. Let me just double check that. But why a pyramid, right? And does this then? Because obviously, the Great Pyramid is also 4-sided. Is this another clue that we should follow down on? I mean, because the thing is this: when it comes to the mystery schools, right?
I want to know if the total of its sides equals pi, like the division of the height and its width.
That's yeah.
Because that's what the pyramid of Cheops is. Yeah,
well, that's exactly it. So I don't know, right? Sorry, the tetrahedron is in fact one of the 4 platonic. So one of the platonic. There are 5 platonic solids.
Yes.
4 phases, 6 phases, 8 phases, 12 phases, and 20 phases. and it's in fact, I guess, the simplest platonic solid.
I think, Mickey, that I'm playing D&D again.
Yes. I love those dice. But yeah,
I've
so
got them
it
in my
is.
house.
Which
My
again,
daughter plays. Yeah.
well, my brother's got all of them.
Yeah.
He's a master. What's it?
DM?
DM?
Yeah.
Dungeon Master.
Dungeon
right?
Master. Yeah.
But the thing is this: it makes no sense. Right? None of this makes any sense. I mean, water. We think of water as just okay, there's water, but recently, and maybe for a little bit now, I've been looking at water and the way it moves, and the way it tries
Fluid
to stick
dynamics,
together.
Mickey.
Yeah, and the way the droplets form, and then I look at it, and then the feel of water, depending on how many chemicals are in there, etc., etc. It's for us, of course, water is life. Very simply, right?
That's right.
It's life, and it underlies everything in our existence more than anything else, because it also contains what we need, not just water but also oxygen, right, to be clear. And
argue that with a fish.
Argue that with the fish. Well, they oxygen, they get the oxygen out of the water.
That's
through
right.
their gill system. So that's the
Even
thing,
though
right?
the water doesn't appear to have anything in it, just looks like water, but there's oxygen in it.
100%.
Yeah.
So it doesn't look. Water makes no sense, right? Water, and this again, we got to go more deeply into it in the next show next week when we talk about the metaphysical aspects of water. But okay,
Mickey,
there's another article. Yeah.
I thought all the mysteries of water had been solved.
Oh, not even close, mate. In fact, as Dave has just pointed out, the couple of studies we've shared with you, nothing has been solved. There have been some theories put forward, and now there are new mysteries of water, in fact, right? With researchers, and thank you for the segue, decoding DNA and smashing open atoms, you might assume the science of everyday water, life's most basic substance, is well understood. And every article I've read on this, every talk I've listened to, that's how people usually start out, right? And in fact, the other one was, despite our dependence, water is a mystery, right? And in this one here, with researchers decoding it, we would think water, well, we figured that one out. Recent experiments probing how water molecules link together have come up with conflicting results, though. Scientists now admit they don't understand the intricacies of how water works. The structure of water, the reason for its peculiar properties, is a major question in chemistry and physics, says Richard Sekali from University of California in Berkeley. And they're conflicting studies here. Water was thrust into the scientific limelight in last April, when a team of scientists led by Anders Nielsen from the Stanford Linear Accelerator Center, we mentioned it earlier, presented evidence that water is more loosely bound than previously thought. The response has not been all that welcoming. A lot of people have a very strong opinion about water, Nielsen said in a telephone interview. At a recent conference on water, some of the attendees stayed up all night debating these results. Sekali was one of them. He calls the result from Nielsen's group a drastic revision of how water is understood. If they're right, they're going to win a Nobel Prize, Sekali told Life Science. But he doesn't think they're right. In the October 29 issue of the journal Science, Sekali and his collaborators published results that contradict the revisionists' findings. There's a lack of understanding. Water makes up 70% of the Earth's surface and is the main component, about 80% of all living things. But it is far from ordinary. The solid form of water, ice, floats instead of sinking. As with most substances, water stores heat very well. And its high surface tension shows how its molecules hate coming apart. Understanding the peculiarities of water requires detailed study of its molecular interactions. We think we understand everything there is about a single water molecule, Sekali said. What we don't understand so well is how they interact with each other. A single molecule of water looks like a letter V, with one oxygen atom at the bottom point and two hydrogen atoms at the tops. These atoms share some of their negatively charged electrons, forming a strong connection called the covalent bond. The oxygen atom grabs more of the shared electrons, which makes it slightly negative, leaving the hydrogen ends slightly positive. This small shift in charge is what attracts water molecules to each other. Say Kelly describes each water molecule as having hands and feet. The hands are the positively charged hydrogen atoms, while the feet dangle off the negative side of the oxygen. Hands can't grab hands, and feet can't grab feet, so Kelly said. But hands can latch onto feet in what is called a hydrogen bond. Hydrogen bonds are 10 times weaker than covalent bonds, but they are the key to water's mystery. Dave?
Breaking the bonds. In ice, each molecule grabs the feet and hands of its 4 nearest neighbours. The placement of these neighbours forms a tetrahedron, or a 3-sided pyramid. When ice melts, the big question is what happens to this shape. The traditional picture, the one that, say, Kelly is defending, is that water continues to look, for the most part, like ice with 4 hydrogen bonds around each molecule. The difference in the liquid form is that at a given time, approximately 10% of the hydrogen bonds are broken. Nilsson's group, in contrast, claims that water takes on a new structure in which a molecule essentially grabs only 2 of its neighbours, with just 1 hand and 1 foot. At room temperature, 80% of water molecules are in this state, while the rest have the traditional 4 hydrogen bonds. The implication of this new 2-bond model is that liquid water would be made up of mostly chains and perhaps closed rings, as opposed to the tighter network of tetrahedrons. Behind the controversy. The 2 groups base their separate pictures on different interpretations of X-ray data. When the X-ray hits a water molecule, it knocks a tightly bound electron out to the edge of the molecule. It is similar to kicking the planet Mercury out to the orbit of Pluto. The physicists measure this knockout energy, which depends on the environment of the water molecule. In a sense, the electron's Pluto orbit acts as a microscope that researchers use to see what types of bonds a molecule has made with its neighbours. Interpreting this microscope data is not easy. However, Nilsson's group used computer simulations, which they verified by testing on simpler substances like ice, which is just frozen water. I'm just going to cold water. When they looked at their water measurements, they found that the computer gave the best fit with the loser 2-bond structure. But say Kelly does not think the simulations can be carried over to liquid water. Say Kelly's group avoided the need for computer models by measuring how the water temperature affected the X-ray measurements. At higher temperatures, the bonds will bend and stretch. The microscope should be able to see that. Nilsson, in turn, does not find, say, Kelly's method convincing. There are many assumptions in his analysis, Nilsson said. He also thinks that, here we go, that the temperature measurements by, say, Kelly's team may be wrong from comparisons to his own group's data. Nilsson and, say, Kelly aren't just scientists arguing a point. They're also friends. And there's one thing they agree on. The debate shows that we don't understand water very well, at least at the microscopic scale, Nilsson said. So Kelly could not think of an experiment that will resolve the disagreement anytime soon. The issue will be unfolding for a while, he said. He also hopes that he and his friend can get together soon over a beer and enjoy some of the peculiarities, that'll do, years, of that watery substance while discussing the matter further. Mekki.
Strange stuff. Water has got some unique properties, as we discussed. Let's just recap. The solid form floats on the liquid form. This property also explains why water pipes will burst when they freeze, something opposite of nearly every other simple substance. Mercury thermometers, for instance, do not explode when the temperature drops below the freezing point of mercury. The temperatures at which water boils and freezes are both higher than other molecules of similar size. Water has a large heat capacity. It can take in a lot of heat without its temperature increasing very much. This makes it an especially good coolant for a car radiator, and it's the main reason temperatures are moderate for coastal communities, as the ocean is slow to cool down or warm up. The high surface tension of water, its tendency to fight being pulled apart, explains why it forms droplets and why it climbs up the side of a straw. It may also play a part in how the water strider walks on water. Obviously, walking on water is possible for quite a few creatures, simply because water is not a mushy liquid or gel that you sink into. There's actually a tension to the surface, which allows lighter creatures, if you will, to walk on it quite easily. But it's really, I think we have time. Yeah,
I think we do, yeah.
So the next article is really interesting, and this was published just last year, but actually about a year ago, July 30th. We'll take it in halves.
What? Have you skipped?
No.
Scientists show that water has memory.
I don't know.
You skipped that one.
No, I haven't skipped it. No. What I haven't done
is shared the new documentation.
No, I thought I did. Because the latest one I sent to you was, okay, you try this one, my friend.
All right.
Is this the one you have?
Well, I'll tell
you.
There you
go. And there you go. Page 16. Scientists transform water into a shiny gold metal. In fact, they found this article. This was written by Nicoletta Lanesi, July 30, 2021. In a mind-bending experiment, scientists transformed purified water into metal for a few fleeting seconds, thus allowing the liquid to conduct electricity. Unfiltered water can already conduct electricity, as we all know, probably, meaning negatively charged electrons can easily flow between its molecules, because unfiltered water contains salts, according to a statement about the new study. However, purified water contains only water molecules, whose outermost electrons remain bound to their designated atoms, and thus they can't flow freely through the water. Theoretically, if one applied enough pressure to pure water, the water molecules would squish together and the valence shells, the outermost rings of electrons surrounding each atom, would overlap. This would allow the electrons to flow freely between each molecule and would technically turn the water into a metal. The problem is that to squash water into this metallic state, one would need 15 million atmospheres of pressure, about 220 million psi. That's a lot, everybody. If you had that much in your car tire,
wow,
it would turn into a black hole.
Well, if you hit a nail, you'd lose half the side of the Earth.
Yeah, I know, right? What? That's probably true. Sorry, this was said by study author Pavel Jungwirth, a physical chemist at the Czech Academy of Sciences in Prague. And he told this to Nature News and Comment. For this reason, geophysicists suspect that such water-turned metal might exist in the cores of huge planets like Jupiter, Neptune, or even Uranus, according to Nature News. But Jungwirth and his colleagues wondered whether they could turn water into metal through different means, without creating the ridiculous pressures found in Jupiter's core. They decided to use alkali metals, which include elements like sodium and potassium, and hold only one electron in their valence shells. Alkali metals tend to donate this electron to other atoms when forming chemical bonds, because the loss of that lone electron makes the alkali metal more stable.
So
alkali. Oh, and this is German. You can say whatever you like.
I know. I'll tell the accent. But do you know what I've learned? You don't put sodium or potassium into water, because both of them have an explosive reaction.
Oh yes, sure enough.
They don't like water so much. But let's use that. Why not?
Why not?
And I also like his term for 2 million psi is ridiculous pressure.
I know.
I want to friend this guy on Facebook. It's really quite funny.
Which brings us to the new experiment, Dave.
Oh, actually, I didn't realize that I was saying what the next piece was. The alkali metals can explode when exposed to water. Yeah. In their new experiment, described in a report published Wednesday, 28th of July, in the journal Nature, I'm going to do a Biden opens in a new tab. The team did just that. In the experiment, they placed a syringe filled with sodium and potassium in a vacuum chamber, squeezed out small droplets of the metals, which are liquid at room temperature, and then exposed said metal droplets to a tiny amount of water vapor. The water formed a 1 micrometer film over the surface of the metal droplets. And immediately, electrons from the metals began rushing into the water. For the experiment to work, the electrons had to move faster than an explosive reaction could take place. Jungwirth told Nature News, and once the electrons zoomed from the alkali metals into the water, an incredible thing happened. For a few short moments, the water turned a shiny golden yellow color. Using spectroscopy, the team was able to show that the bright yellow water was in fact metallic. Our study not only shows that metallic water can indeed be produced on Earth, but also characterizes the spectroscopic properties associated with its beautiful golden metallic luster. Study author Robert Seidel, head of the Young Investigator Group at Humboldt University of Berlin, said in a statement, "You can see the phase transition to metallic water with the naked eye," he added. "It was amazing, like when you discover a new element," Jungwirth told Nature News and Comment. And do you know what? I made him a Southern Californian in the 80s, just then.
Yeah, that's funny.
It was amazing, like when you discover a new element. Sure.
Oh, since this is the only rendition of a Southern California I've ever heard, it must be the best one.
Well, I went to school in the 80s in Southern California, and
Nice.
some of my friends were surfy dudes, and they absolutely spoke just like, what's his name from that movie? I'll get there.
Fast Times?
Yeah,
Fast
at
Times,
Ridgemont High.
It was the actor was brilliant. I
Sean
like him
Penn.
still.
Sean Penn. Yep.
Sean Penn. Yeah,
He played Spicoli.
Spicoli. Spicoli! Yes, dude. Chill out. My brother's got this rad set of tools. Can he fix it? He can fix it.
Totally fix it.
He can totally fix it, man.
He's a television repairman. He can totally fix it. That was the Trans Am that they smashed.
I love that. Anyway, no, but isn't that astounding? And you know what really gets me is well, the metallization of elements is. I mean, yeah, we know that happens. It can happen, given enough pressure, etc. But it's the color. It's this golden luster that water metal has. I find quite interesting. It makes you wonder. Let's say you have the right conditions for water to exist in metallic form. What properties could one imagine this water would have, or this metal would have? I mean, is this the stuff of life? Is this on the route to monoatomic elements?
It's close, isn't it?
Well, I wonder. Because, I mean, gold itself turns into a powder under certain conditions, which seem this powder seems to negate gravity. It seems to also phase shift, oddly enough.
That's monoatomic elements.
Yes, correct. This was actually the first show we ever did. We should revisit it. But now seeing that water could be turned into this golden metal under the right conditions, it makes you wonder what that could lead to. What kind of properties could could be observed, and what kind of uses that metal could be put to.
Well, if it's metal, then it might have magnetic properties.
Potentially.
Yeah.
But it can only exist under this enormous pressure, right? So if you could somehow stabilize it in its metallic form without requiring this pressure, like for example, diamond is formed under enormous heat and pressure, we think, right? But then it's stable, then it's formed. I wonder if water, once it has formed into this metal or metallic substance, would equally be stable.
Yeah, whether it turns back or not. Yeah, of course.
Yeah. So I don't know. Again, I find this endlessly fascinating. And again, to me, water is as mysterious as the moon, and it makes no sense. And I always find it very difficult, Dave, to deal with things that I don't understand. Right? I feel like if I can't understand it, if I have no hope of understanding it, then it bothers me. I need to understand why it happens or how it happens. And once I understand, I'm good. Then I'm good. Whatever. It doesn't even matter what. As long as I understand, someone tells me what it is, or something, some insight comes to me. Brilliant. But right now, it is just another thing that just scratches at my brain. This water thing.
I think you science, Mickey.
I'm sciencing.
Sciencing right now.
It is. Actually, my daughter said this yesterday to me. I know we've only got a few moments left. I don't think we can get to the other. Oh, no.
That's right.
Because this is a whole topic. Because we want to go into this in some detail. So it's the next week, before I go into launch to my story, we're going to talk about the theory that water has memory. So we're going to talk about that. We're going to talk about a double-blind test that was conducted as well. We're going to talk about Dr. Masaru Emoto, a pioneer in that area, and then we might find some more mystical sides to the water, as well as some stories around water.
I'm activating rivers, Mickey, is what we're doing this
I
week.
know. Yes. My daughter said I should be a scientist because I was explaining things to her. She asked me, how does this work, how does that work? And I said, well, this is how it works, but look, we don't know about this. Because she's not old enough. She's 8 years and the other one is 6. So they understand more, right? So they ask questions which are, more, not more meaningful, but they're deeper questions. So I try to explain this as best as I can. The rabbits and why the Chinese
the rabbits comes from a TV commercial. It's very funny.
to keep the rabbits out. So sure, you should have been a scientist. And I said to her, well, I did. I remember this was my first day at Sydney University. I had gotten into economics because my parents, or my father specifically, said, look, what do you want to be an archaeologist for? That's just silly. Can't make any money there, right? Like, okay, well, even though you think you're independent, you still listen to what your parents say. My father, specifically here. So I did. I applied for economics, got into economics, but I was there, and I could have taken archaeology as a side subject because I could have taken economics as an arts degree, right? But I didn't, and I regret it because that would have been a path I would have very much liked to have walked down. Not much money in it, I guess, but probably more suited to my temperament. So it's the road less traveled, and I find science to be the best way to explain the natural world that we have come up with. However, as I've said many times before, and I will keep saying it, we need to find other ways to explore the natural world that don't, or that the parts of the natural world that don't lend themselves to the scientific method. And we know, again, I come here. Here comes Dave. Skinwalker Ranch, right? Places like that on the planet.
Charge your glasses, gentlemen.
Charge your glasses. Which are simply impossible to explain with the scientific method. We can't. This is our limitation. We can explain many things. And it's an awesome mechanism, an awesome tool in our arsenal. But we must devise other. We must devise other methods, methodologies, processes to explore and examine those phenomena which are not easily examined using the scientific method. We have to, because they exist, and they don't comply. They don't always react the same way. So if you do something once, it might have a certain outcome. You do the very same thing again, and another outcome happens, or nothing happens, or then something so opposite of what happened initially happens that you don't even know where you're at anymore. And this is really the problem. Well, it is, right? We
Sounds
don't
like quantum world.
There you go, buddy. That's exactly right. And to try to look at because it's a field of probabilities. You see, that's what we're walking on, this field of probabilities. Some things, some outcomes are more likely than others, right? Simply based on the timelines, and I mean this for all of us that we're on, or the perceived timelines we're on. Whereas other outcomes are completely impossible on the timelines we're on. But again, all of that, I think, again, is a complete illusion. Because in our true state, I think we are quite limitless and aren't at all bothered by things such as timelines and probabilities.
If you look at my face, I ain't bothered. Hey, guess what, everyone? That's the end of the show. I can't believe it went so fast. Coming up next is Gerber. It's an awesome show, After Hours. Stay tuned to become part of it. And what we're going to do, we're going to see you next week. We'll see you on Tuesday night and Thursday night and also on Sunday. So catch us on Plato's Cave or Shiny Side Out. And we'll see you next week.